Next we need to talk about something called a Riemann sum. And for us to work with Riemann sums, we have to be looking at some continuous function y equal f of x, and this function has to be non-negative on the closed interval from a to b. And a Riemann sum can be used to approximate the area trapped between the graph of the function and the x-axis on the interval from a to b. So in the picture you're looking at there, the region R would be this region. Now, we have to start by taking that interval from a to b and dividing it up into some number of subintervals that are all the same width. So we're going to divide the interval from a to b up into n equal subintervals. Here's kind of how you have to think about that. Delta x is going to end up being the width of all the subintervals, and you can figure out exactly the value of delta x by taking b minus a, which is going to give you the total length of the interval, and dividing that into n parts. So you can always find the value of delta x by evaluating b minus a over n. Alright, and then here's how we're thinking about this. We're going to let x sub 0 be the endpoint a. And then we're going to go delta x units to the right and get to the point x sub 1. So this little amount of space right there is delta x. And then we're going to go delta x units to the right again to get the endpoint x sub 2. So that length is delta x. And then we're going to go delta x units again to get to x sub 3. And so on, and so on, and so on, until we get down to the end. And where we'll have x sub n minus 2, x sub n minus 1, and finally the endpoint b is x sub n. Now the endpoints of these subintervals are called grid points. So in this particular case we're talking about grid points that are labeled x sub 0, x sub 1, x sub 1 comma, x sub 2, and so on and so on and so on. The last grid point is going to be the endpoint x sub n. When we divide an interval up into n equal parts, what we've done is we've made what's called a regular partition. In general, the grid point for the kth, no, I didn't lisp. Let me back up. For the kth interval, the grid point would be x sub k, and you can find that by taking the endpoint a and adding k times delta x. Now think about that. To get x sub 1, which would be this grid point right here, you would take the grid point a and add delta x. To get x sub 2, you'd take a and you'd add delta x and delta x. To get x sub 3, you'd take a and you'd add delta x, and delta x. So to get x sub k, you would take the beginning endpoint a and add delta x to it k times. Now, to make sure that you understand about grid points in a regular partition, let's take a look at an example. Suppose we have the interval from 1 to 9, and I want to divide that up into 4 equal subintervals. Start by figuring out what the width of each subinterval is. Find delta x. So 9 minus 1 divided by 4. And if you do that arithmetic, you're going to find that the width of each interval is going to be 2. Alright, then the grid points for that interval, x sub 0 is going to be the point 1. To get the point x sub 1, you're going to add 1 plus delta x, so that would be 3. To get the endpoint, the grid point x sub 2, you're going to take the endpoint 1 and add 2 times delta x, so that would be 5. Okay, and you can just simply add 2 to each successive grid point to get the others. So x sub 3 would be 7, and the last grid point, x sub 4, would be 9. That 7 comes from 1 plus 3 times 2. The 9 comes from 1 plus 4 times 2. Now, so that's how you start, by partitioning your interval. So let me do that, and I'm not going to be able to squeeze in very many endpoints here. I'm trying to make these intervals as regular as I can, and that'll be good enough. That's close. So I've divided this interval from A to B up into 6, 1, 2, 3, 4, 5, 6 equal parts. And what that does for us is it allows us to kind of section off the area that we're trying to calculate into little strips. Alright, now the next thing you do is in each interval, we've got 6 of them here, you're going to pick some sample point. And the sample point we denote, if we're talking about the kth sample point, that would be x sub k with a bar. Now, that sample point can be any point in the interval. So if when we look at the first interval, I might choose that point right there for my sample point. So that's x sub 1 bar. It's the sample point in the first interval. And in my second interval, I might go way over close to the right endpoint. So there's sample point x sub 2. You could choose a midpoint for your sample point. You could choose an endpoint for your sample point. Okay, but basically you just have to select some sample point from each interval. And then what we do is we're going to plug that sample point in to the function to determine the height of the rectangle we're going to use to approximate the area under that curve. So bear with me while I get that picture drawn. So I'm going to plug in the first sample point. So that red line there is going to be what I use to approximate the height of that rectangle. And then I'll plug in the second sample point. And that red dotted line there represents the height of the second rectangle. And then I'll plug in the third sample point. You get the idea how this is going to work. I'm going to pause the video and draw the rest of this in. So now we're going to actually calculate areas, and the area of the first rectangle would be found by taking the first sample point, plug it in into the function, and then multiplying that by the width of that interval. Each of these intervals is going to have a width of delta x. The second rectangle the area for that rectangle is found by substituting the second sample point into the function and multiplying by delta x. The third rectangle, the area for that rectangle is calculated by plugging in the third sample point and multiplying that by delta x, and so on. Alright, so what you see there is the sum of the 6 rectangles that are used in this example to calculate the area under the curve. This is called the Riemann sum. Now, because the sample points can be any points in the interval you want to, it is logical that you might want to choose kind of the same point in each interval. And you can, if you pick the left endpoints for each interval, you'd have what's referred to as the left Riemann sum, which, when you think about what we've done earlier in this lesson, that would be the same thing as a left rectangular approximation. If you pick the midpoint for each interval, you're looking at a midpoint Riemann sum, which would be the midpoint rectangular approximation. And if you pick the right endpoint in each interval consistently, then you'd be looking at what's called a right Riemann sum, which is the same thing as right rectangular approximation. So what we started with, which was just thinking about rectangles to approximate area under a curve, now we've gotten a little more specific, and rectangular approximation using the left endpoint or the right endpoint or the midpoint is just a specific Riemann sum.